Hi all, this video is about composition of functions. So we've been learning about functions and working with them a lot. And the focus here is ways to combine functions. And there's actually a ton of ways we can do that. Some easy examples are adding two functions together, subtracting two functions, multiplying two functions, dividing two functions. And a really cool fact about any of those is that when you do that, what you end up with is also a function. It might have, especially if you're dividing, it might have some effect on domain restrictions and things like that. But in general, if you add, subtract, multiply, or divide two functions, you will end up with a new function. There's another way that we can combine functions that's a really important one for us. We use it a lot. It's called composition of functions. So the idea would be that we take the x value, plug it into one function. Whatever we get out, we plug into the next function. And actually, you can use the same function twice, totally valid. So here I typed some of these up at the top of your packet if you want a little bit more precise definition. So again, we're taking two functions, we're plugging something into one of them. Whatever we get out, we're plugging into the other one. And the final output is the output of our composition, and the very first thing we plugged in is the input of our composition. So we're going to practice a lot of this. First thing I think we need to know is about the notation. So hopefully that's clear with the little circle. If we want to compose functions f of g, f and g, the way we would write that, there's actually two ways. That's the first one. That's a little circle in the middle. It's not an O, it's not a times, it's just a little bitty circle. Means composition. This means exactly the same thing as writing f of g of x. So I think these notations both have some strengths. Both of them are telling us that we would take an x value, plug it into function g, take whatever we get out of function g and plug that into function f, and the final thing we get is our output. So there's this two-step, we have to work through two functions. I like the first one that it really emphasizes the fact that what we've just ended up with by composing two functions is a new function. So this is the name of the composite function. So it really emphasizes that when you compose f and g, yes, that means plug into g and then plug into f, but really important is the fact that what you've just done is created a brand new function, and it has kind of a messy looking name, but that's still a function name. So f of g is the name of the composite function that results from composing functions f and g. I like this one because it really, I think, clarifies what exactly we're supposed to do. Parentheses, you always want to work from the inside out, so we would plug in x into g. We would then take whatever we get from g and plug that into f, and then we get our final output. I think this one also makes it kind of easy to see why we call the two what we do. So we would usually say here the first function that gets the x value is the inner function, and the last function to get the, it doesn't get the x value, it gets the output of g. The last function that we use is the outer function. Conveniently, it's always written in the same order for both notations. So basically, x gets plugged into whichever function it's next to first. One kind of tricky detail that won't come up a lot in my first example, but we'll work our way up to it, is domain. Domain is a little bit tricky. When you put two functions together, again, what's happening in something like this is we're taking an x, we're plugging it into g, we're taking whatever we get out of g, the output of the inner function, and we're plugging it into the outer function. So what happens is it doesn't make sense to try to plug something into the composition if it's not a legal input for g. So we're starting with the possibility of any of the inputs for g could be in the domain of the composition. The problem is there may be inputs, x's, that we plug into g that give us outputs, g of x's, that are not legal to plug into f. So there's kind of a two-part check. One, we have to, for starters, make sure we're in the domain of g, or we won't even survive the first step of plugging into g. Two, we need to check that whatever x we started with doesn't lead to a g of x that we're not allowed to plug into f. So this ends up being not that painful to check, but it's a little confusing to people at first sometimes. So I'll try and make sure I say that multiple times and hopefully it'll make sense. Okay, so that's really all we need for background info, and then it's just a matter of practicing. So I'm going to start with two, I think, fairly simple functions, a linear and a quadratic function. And I'm going to start just by plugging in specific values to make sure you're really clear on how this works. And then we can go ahead and start trying to build formulas for compositions of functions. So that's our goal, and talking about their domains. Okay, so on this one, we want first to find g of f of 4. So if we want to use the other notation, and my expectation would be that you understand what both of these are, so you can use whichever one you want. If I use one or the other, it should not confuse you. So this notation, I think, more clearly guides me through the steps. I'm supposed to find an f of 4, which means go back, plug 4 into f of x. When I plug 4 into f of x, I get 3 times 4, which is 12, and then I add 1, and I have 13. So f of 4 is 13. If I then plug 13 into g of x, I get 13 squared, which is 169, plus 5, which is 174. Okay. Sorry, spacing out, looking at my notes here. The next one is f of negative 1. If we want to rewrite with the other notation, we get this. F of negative 1 is 3 times negative 1, which is negative 3, plus 1, which is negative 2. So we're supposed to plug a negative 2 into the outer f. So again, it's completely valid to compose a function with itself. And again, what you come up with is a brand new function. It's not just function f anymore. It's now called function f of f. If I plug the negative 2 into function f, I get a negative 6 plus 1, which is a negative 5. Okay, g of 2, we're supposed to take the 2, plug it into g. So we will get 2 squared, which is 4, plus 5, which is 9. When we plug 9 back into g, we get 9 squared, which is 81, plus 5, which is 86. Okay, so this is how we do it point by point. And basically what we've just determined here is that we now know a point on the graph of g of f for this first one. And that point is 174. So it's really important that you filter out what the most important information here is. We had to calculate the 13 in order to get our final output, but 13 is not an input or an output for the composition. The input we used for the composition was 4. The output we got for the composition was 174. And again, the 4 has to be in the domain of f because that's the first function it gets plugged into. Whatever I get back, the 13, better be in the function of g or I'm going to be in trouble there. The final thing I get out of function g, so my final output is always from the outer function, is this 174. So the 174 is something in the range of the composition. If I want to talk about the graph of y equals f of x, I've just discovered that that function goes through the point -1, -5. So again, the key pieces of information for the composition are the very first thing you plug in and the very last thing you get out. In this case, we're only working with f, so both of those are coming from function f. The last one is g of x. If we're talking about input-output pairs for g of g, we input a 2, we output an 86. Okay, so we can do this. We can plug in whatever we want, and we can work our way through the inner function, get an output, plug that into the outer function, work our way through, simplify, get the final output. But it's kind of convenient to be able to collapse this down and just find a formula that describes everything that happens to x by the time it's gone through both functions. So this is going to be our big goal, is actually building up formulas that will give us input-output pairs for the composition. Really, all we have to do to build up these formulas, so if I want f of g of x, is not choose a number ahead of time and just keep our variable x in the mix. So if I take an x value and I plug it back into g is still this guy way up at the top, I'm going to get back an x squared plus 5. If I then take the x squared plus 5 and plug it into f is going to multiply it by 3 and add 1. So I am getting 3x squared plus 15 plus 1. So f of g of x is 3x squared plus 16. Oops, got an extra parenthesis. Okay, so this formula should now take me directly from input that goes into G to the output that comes out of F. And we already did one of these, so we can double check it. Let's see our F of G. Oh, I lied. We didn't already do one of these. So if we use this function, F of G, let's plug in a 2. The formula we just found says we should get 2 squared, which is 4, times 3, which is 12, plus 16, which is 28. This should entirely always agree with what would happen if we went f of g of 2 and did it the two-step way. Plug 2 into g, we get 4 plus 5 is 9. Plug 9 into f, we get 9 times 3, which is 27, plus 1, which is 28. So you can see it should give us the same answers, but it saves us from having to plug into 2 different functions. It collapses down, and it turns out if you take your x, you square it, you add 5, you then triple that and add 1, the result is just 3 times the square of your x value plus 16. So I deliberately for this first one picked something that doesn't have a lot of trickiness going on with domain and range, but I still want to talk about it so that you're thinking about it. I won't always be wanting to ask you about range, but I think it's really interesting to look at here if we're understanding what's happening. So what's going on is that there's this set, the domain of G. And we're starting with numbers that are in that set. G is our inner function. It's the first one that we plug into, x's. As we're trying to follow this x through, it gets plugged into G. So this is function G gets it. And it gives us back something that's in the range of G. We then have to be really careful because we're going to plug that number into F. And if F has any domain problems, we might have to backtrack and leave something out of this first set. So if we run into any numbers here that give us problems, we have to figure out how to eradicate them way back at the very first step. Again, I've been nice to you on this one. I picked functions that don't have a lot of domain problems. So function G, the domain of G, G is this quadratic. This is really all real numbers. It doesn't have any domain problems. I can plug anything I want into G. Conveniently, the same is actually true for F. I can plug anything I want into F. I'm not going to have any problem. So there's no reason for me to leave anything out in the first step or the second step. But the range is kind of interesting here. So I plug in all real numbers. I don't get back all real numbers from a quadratic. If we're thinking y equals x squared plus 5, this is a parabola shifted up 5. So my range is going to be numbers, how do I want to write this? Numbers greater than or equal to 5. We'll just do some sloppy shorthand. I don't want to put a y variable there because I'm thinking of the very last thing I get as a y, and this is just kind of the middle thing. So you could give it another variable, but I'm just going to say what makes it out of G are only numbers greater than or equal to 5. So the domain of F is actually bigger than the range of G. The domain of F is all real numbers again. We can plug anything we want, that's not off, that's domain of f, into function f, but we're not getting all real numbers. We're only getting these numbers. So we lose a whole bunch of inputs that would have been legal to plug into function f. So now we're only plugging in numbers bigger than 5 to function f, which means we're not going to get the entire range of f in this case. So f is a linear function. Again, having pictures in your head is really helpful. It has a y-intercept of 1 and a slope of 3. So it's going along something like this. If we plug in any real number, we can get back any real number. So if we have access to all real numbers, we will get back all real numbers as y values. But we don't have access to all real numbers. We only have access to real numbers. This is a funny scale, but just pretend that's 5, greater than or equal to 5. So if the things we're plugging in are only out here greater than or equal to 5, the things we're getting out will all be above this point. Since this is y equals 3x plus 1, this point right here is 5, 16, just plugging the 5 into the equation, which means we're only ever going to get our final y values. So this is the range of, what were we doing? F of g. We're not going to get the whole range of f. We're going to get part of the range of f. We're only going to get the part where our y values are greater than or equal to 16. Okay, so I don't think this is anything too crazy exciting in some ways, because we could look at this, and if we thought about transformations carefully, we could come to the same conclusion. But understanding this whole two-step process where you plug something into one function, you get something out, you plug it into the second function, and there's these two sets, the range of the inside function and the domain of the outside function, and we can only work within the overlap of those two, which can restrict both the things that we're allowed to plug in and the things we'll finally get out. Okay, so that's our first one. Thank you for watching.